and welcome to Drones Flying Through 2017. We're so thrilled to have you with us today. We have folks from at least 90 countries, more than 1,700 of you have signed up, and we are just glad to have you. Before we get started, we owe a huge thank you to Blue Marble Geographics and Rock Technologies for being gold sponsors with us today. You can expect to hear more from them later. Also, we're honored to have AUVSI excuse me, sponsoring our event. So do stop by drones.directionsmag.com to get more information from those sponsors, as well as all of the links we're sharing today. We are honored to be co-hosting with the good folks over at the Geotech Center. We like doing things with the Geotech Center. They're great folks. I'm Barbara Duke, Managing Editor here at Directions Magazine, and we have been around since 1998. Providing news, original articles, and of course our webinar program. We encourage you to stop by our UAV channel, and again, we've got links to share with you. Do take a peek over on your webinar control panel. There's a handout section. We've got a couple of things to share with you there. I'd like for you to meet Rich Schultz. He is working with the Geotech Center, as well as a university professor, instructor. I think even he's moved further up the food chain, but I know Rich just because of GIS. And so we're thrilled to have you with us today, Rich, and tell us a little more about yourself and the Geotech Center.
Thank you so much, Barbara. It's a pleasure to be on webinars again with Directions Magazine. We've done this in the past a number of times, and we've always had great experiences and very educational webinars. So we're looking forward to our last session today. As Barbara mentioned, my name is Rich Schultz, and I'm the Associate Director for the National Geospatial Technology Center of Excellence, also known as the Geotech Center. Our website at geotechcenter, all one word, .org, where we have the National Geospatial Technology Programs map. We are responsible for providing the Geospatial Technology Competency Model, or the GTCM. We have some curriculum that is freely available, as well as model geospatial courses, a personal assessment tool, which is a great tool to be able to assess where you might need some additional educational training or professional development in the area of geospatial technologies. We have a syllabi repository and a number of other valuable resources. The Geotech Center is headquartered and located in Louisville, Kentucky at Jefferson Community and Technical College there. And with that, I will hand it back to Barbara, and we're off and running for a terrific webinar here today.
So now we're going to dive into sort of the nuts and bolts and software that helps make sense. We are going to start with Peter. He is coming to us from Colorado and is an experienced drone builder, and is going to talk to us at length about, what makes good sense. Peter, over to you.
Thank you. Thank you. Thanks for the opportunity. I'm going to try to share some of my experiences from constructing UAVs. I come from a background in high precision GPS, precision agriculture, wireless telemetry, embedded systems. So I'm coming at this more from the technology side, and a lot of my interest driving learning to build UAVs started early when there weren't as many commercial solutions, and it was really driven to test the technology that I work with every day. Hoping that I can provide some starting places for folks that have interest in building, to get you going in the right direction for your learning process. There is a lot of research and a lot of different ways to go about this. So the internet is your friend, and there is tons of resources, but hopefully I can provide some starting places and narrow things down a little bit. Building them yourselves is an excellent way to really understand the systems involved. You can be aware of a lot of the factors that go into automating these systems, and that can be pretty helpful, whether you're doing it for fun or doing it for real work. So building versus buying. why might you want to buy versus build? Well, you might have some special needs. You might be ready to just head off, start collecting data. You don't have time. You've got a goal to accomplish. You've got the budget to buy a commercial system, and you may just go straight off to the races with a commercial solution and really focus your time on optimized flying of that craft to get your data collection faster. And that's a very common approach. It depends on the type of work you're doing and the interest you have in all of this, and just kind of your rate to which you're dipping your toe into the water. You might also have some kind of complex automated missions to fly. Situations where you might have, for example, really varying terrains. You want to have a common ground sampling distance, and the software provided with a lot of commercial solutions will really help you automate those flights. Let's talk about building. That's what we're going to talk about today. Oh, sorry, I forgot to mention integrated workflow. A lot of the commercial solutions really tie you into the next steps of processing those images and turning them into the models, the deliverables, the things that you're trying to accomplish by flying the drone in the first place. So why build? It's fun. Build skills, gives you an appreciation of what the whole system does. You might have a special payload. You might have a special sensor. Maybe you aren't even collecting imagery. You are trying to fly some other type of sensor, heavier payloads, and you want to be able to adjust the craft to your needs. Building your own gives you ability to upgrade it kind of along the way, or do little bits of maintenance, whereas a commercial solution you might be limited just to kind of very big parts replacement if you had to. And maybe you have some sort of special automation that you want to do. You gotta create a very unique set of tasks or scripts or something you need your craft to do, and you may be only able to do that in a situation that you've in a craft that you've built. Cost. That one's a tough one. Yes, it can absolutely be cheaper to build your own. You end up spending a lot of your own time filling in the knowledge gaps to get proficient at it. So it totally depends on your approach and kind of how you're treating your time in the building process. We commonly think of three types of aerial drones these days. Probably familiar with fixed wings and multicopters. What I'm leaving out here is traditional rotorcraft. I'm not going to cover that. It doesn't tend to be as much of a camera platform. Tends to be more of a workhorse for automating other tasks. But so let's compare multicopters and fixed wings. Multicopters are kind of nice because they allow you to build and test in a real limited area. You don't really have to think about too much space around you while you're getting up to speed, and that can be really valuable if you have to travel someplace to gain space to be able to say operate a fixed wing. The multicopters are less sensitive to payload, and that's depending on what you're loading on there. It may be real handy just to be able to zip tie something on there. And a stabilized video platform. Multicopters are better. Fixed wings really stand out in covering large areas, capturing downward facing images, and doing this very efficiently. You've got a couple hundred acres to cover. You may be able to accomplish that with a single mission in a fixed wing. So it saves time in the field, and it's typically a simpler craft to operate from parts and electronics. But you do have to worry about the areas for takeoff and landing, the space again. With all that said, I'm going to focus on multicopters today just to give you one path through kind of the build process. There's a lot of carryover between those two, so knowledge isn't wasted. On this page, I've kind of just taken a multicopter here and pointed out some key components. I don't know the degree to which everybody may or may not be familiar with these, and I just want to kind of put some common ground. But we've got GPS and compass in here, batteries, motors are fairly obvious. The electronic speed controller that turns DC power into three-phase AC for these motors. That's part of all these craft. You have a flight controller, the central brain of the device. You have your RC receiver, and you may have a telemetry receiver as well. A gimbal and a camera for your platform, propellers, RC controller, and then very likely you'll have a laptop running some ground control software and a telemetry radio. It's not required. You can accomplish quite a bit by programming your RC controller, but I think this makes a lot of sense to start thinking about this early in the learning process. Here I broke out kind of just some of the major pieces and pointed out some names, some places to get started, some vendors to look at, some brands to look at in the components. Here's telemetry radios, GPS, and I'm really focused on the Pixhawk flight controller, autopilot. There are many different autopilots out there. This one has a large following, lots of users, lots of good forums, lots of good data, tutorials, support available, the mission planner, ground control software to go with that. Tiger motors, ESCs by Tiger as well. I've been using some frames by Taro. And my radios of choice these days have been the FR Sky radios and receivers. By no means is this an endorsement, it's just some parts that are kind of my go-to parts and a starting place for your research. Let's see, I put out a schematic here just to kind of give you an idea of how everything is interconnected. It's pretty high level. The flight controller is the heart of everything. And here's your RC transmitter providing flight controls to it through an RC receiver. There's that ground software and telemetry radios talking to the flight controller. We have sensors that the flight controller uses, GPS, compass. The flight controller itself has the sensors built in, accelerometer, gyro, barometer for altitude sensing. We have a battery. We've got to distribute power to all the different components, the electronic speed controllers, one each for the motors. And in this schematic, we're calling out kind of a quadcopter here, but this could just as easily have 6 or 8 motors for a hex or an octocopter or an X8 or one of the different layouts that are available. A build process. I want to try to provide some approach at kind of organizing your thoughts. You know, you can go onto the web and just get lost with where to start. So some of my suggestions are pick a goal. It could even be I'm going to build a small throwaway craft just to learn the whole process. But having a goal in mind really helps you pick parts and pick the size of parts that you need, your frame sizes. You can come back and repeat this process with your next build and have a different goal or target in mind. Parts, you might have to buy parts from multiple different vendors. So you might be assembling, it's not that they're incompatible, but it's very rare that one vendor seems to have everything in stock that you may need. I would start with kind of familiarizing yourself with the RC transmitter and the receiver and its features. Basic setup and programming from instructions available on the web, and then move on to almost building your craft on the bench. Connect all the pieces. Start with the autopilot in the center, and don't worry about wire length and how it looks or anything like that. You're just trying to connect all the parts, make sure that things are recognized, sensors are recognized, ESCs operate, kind of a conference room pilot version of the project before you go back and really assemble it onto the frame, route wires efficiently, pick your locations for the batteries, things like that. Ground control software likely has a setup wizard that really helps with the calibration. I'll talk a little bit more about that later. I guess the safety item here, don't install props until you're really ready to fly outside in a safe area and you've done a little bit of testing. And wait to add the camera till after you've got a craft flying and it's you've got some confidence in it. You're likely going to crash one of these or have hard landings as you're going up the learning curve, so it's probably doesn't make sense to damage a camera early on. What are some build tips? Some things I've learned or I guess followed as I've built these craft. The sensors may need to be located away from electromagnetic interference. Mainly the compass is one of the key ones. Also the barometer to try to avoid pulses of wind. So pay attention to that as you're locating the components. The ground control software has a configuration wizard. Take advantage of that to calibrate all of your sensors. Get your compass calibrated, get your accelerometers calibrated. It'll walk you through the process. I would start when you originally set up your craft with just 2 flight modes, stabilized and position hold. I wouldn't touch any of the automated modes until you're more familiar with the craft. There is a tuning process. I found though that starting with the APM or the PickTalk flight controllers, that the stock parameters for tuning are pretty good and get you into the air. But you're tuning a control loop with commonly known as a PID loop, and there's some auto-tune features that are available and might speed up that process. But try the defaults first. A lot of time can be spent in the tuning process, and it's probably worth it. But reading up on it can help you do that efficiently. Be sure to test the endurance. Don't surprise yourself by being far away or high up in the air when your battery really starts to decline. Really know the limits of your flight and run timers so that your craft doesn't fall out of the air. Fail-safes, there's a number of fail-safes that can be built into things. Geofencing, low battery automatic landing, what the craft should do if you lose RC control. So be sure to set those and test them, know what they do. Adding a camera. Boy, there's a bunch of different camera options out there. A GoPro is a really good place to start. You probably already have a GoPro. There's all sorts of accessories for mounting those. That may be a simple place to start just for the practice of collecting some aerial imagery. Commonly a camera is stabilized by a gimbal. This one up top is a brushless gimbal. This one on the bottom is just a kind of a vibration damp mount that allows you to aim the camera with the RC controller. Triggering the camera. Depending on the camera type, you're going to have to find the appropriate cables or maybe even a little circuit. And these are commercially available so that the flight controller can give its signal to trigger the camera capture or the image capture. And if necessary, the camera can send the confirmation back and tell the flight controller when the image was actually captured. Specialized cameras for doing, say, agriculture applications. There's some real specialized cameras out there, and you may want to start looking into those. Basic operation. I would say get it in the air and try out position hold. You really can then kind of let go, and instead of having to control it, you can position the craft in the air with very little control input. It's a good place to start familiarizing yourself. From that spot, you can oftentimes just trigger and capture images, and you may be able to accomplish a lot of what you're trying to accomplish with just this simple of a setup. Aim the camera straight down, position the craft where you want it, capture an image, bring it down and see what you've got in your data. Quickly here, I'll go through some automated missions. This is using that ground control software to really automate the image capture for a larger area. So this is hands-off flying, letting the craft go out and capture images, fly a pattern. Really got to learn the ground control software to do that. Starting with simple missions, just get it in the air, allow it to fly to a point, fly back, convince yourself that it works. In general, you create a flight plan and upload it to the craft, and then switch it into auto mode, and that kicks off the mission. Some knowledge of the product you're trying to end up with, the ground sampling distance, the resolution they're trying to end up with in the final model or mosaic that you're going to build will help you plan like altitude of the mission, and it's helpful to know the camera parameters to choose that. You can run telemetry while the mission's going on. That helps you monitor it, maybe make a change, and the ground control software often helps you take the final step, geotagging your images after the mission, and then starting to move those on into projects for processing software. And we're going to hear a lot about processing software after this segment, but the Pix4D or some of the Autodesk Remake, Agisoft, and then of course Drone Mapper. Lastly here, I just included a slide that you can come back to later. Some starting places, some places on the web to start reading and seek out tutorials and forums to get you pointed in the right direction. So I think at the end of this we're going to have some questions, so I'll be online then.
Great. Thank you very much. We really appreciate you sharing your expertise. And we're going to shift gears and talk software. So we're going to welcome back David McKittrick. And he is going to share with us some good information from Blue Marble.
Thank you, Barbary, and thank you to Directions Magazine for putting on this excellent event. We were so happy when we heard about this, that sharing a little bit of what we're doing at Blue Marble with the UAV community. Oops, let me fire up my PowerPoint once again with apologies. Decided to end on me here. Click the right button this end, there we go. David McKittrick, my name, Senior Application Specialist. Those of you who do not know Blue Marble Geographics, we're a software company. Right now I'm looking at my window with a lot of white on the ground. So we're in the state of Maine, up here in the northeast. We're between snowstorms right now, so it doesn't look too bad looking out the window right now. But we're a small software company. We produce a couple of products, Geographic Calculator, which is a geodetic toolkit, and of course Global Mapper, and that's what we're going to be taking a quick look at today. Interesting story about Global Mapper and its relationship, if you like, with the UAV community. We didn't actively seek out that market for our product. It found us, and we're hearing increasingly on a day-to-day basis about folks who are using this software in their operations, and in truth, we're learning about this technology as well. It's a learning process for us, and we're adapting our software to meet those needs. So my 15 minutes of fame today, I'm going to quickly go through a high-level overview of the software. I won't bore you with PowerPoint. I want to actually get into look at a couple of scenarios, time permitting, where we're actually going to look at some data. We're going to look at some UAV collected data and what you can do with it within the application. So let's first of all take a quick look at what exactly the software is and specifically how it works for the UAV community. Well, obviously for flight planning, initial flight planning, basically give me a reference framework that I can work from. And here we have the little screenshot of just drawing perhaps an area that you're interested in surveying. Data management. This is probably the key part of the application, the ability to ingest your data, process the data, work with whatever format data you want, and as you'll see when we get down to the end of my bullets here, I'll ultimately export that data as well. Global Mapper supports 250 formats of data, so I can guarantee that the type of data you either ingest or export is going to be supported by the software. Major part of what we're doing in the software is point cloud processing. LiDAR is the common format, but basically any point cloud. And in fact, my workflow scenarios today are going to focus on extracting intelligence from point cloud data. Derived from that point cloud, you could be someone who works with terrain, perhaps, generating a terrain surface. A lot of people like the idea of just generating some contour lines, and you can see on my little screenshot again the creation of vector contour lines. Again, if your workflow requires you to generate those in a CAD format, a KML file, or a shape file, very easy to process those from the software. Terrain analysis, we've got a surface model here, again, derived from some point data, and from that we can, again, apply intelligence. We can do an analysis of volume. We can conduct a calculation. We could generate a watershed model or create a viewshed model, all derived again from that source data, that point cloud data. My first workflow that I'm actually going to show you when we get into looking at the software is an extraction process. Now there are multiple flavors of that available. Vegetation extraction, building extraction. The one that I'm going to show you is actually utility line extraction. You can see a little screenshot again, a little teaser here. We'll actually take a look at the software in a minute and show you how this process works, where we can identify linear features above ground, utility lines, and extract those as vector features, as three-dimensional vector features for whatever your GIS or mapping work requires. Another part of the software which is very, very useful for UAV operators is simply project visualization. The simulation you're seeing on the screen right now is a video, obviously it's a static image, but over on the left, kind of off screen, is a video of the terrain underneath my flight path. So we can actually play back the path taken by any aerial vehicle, whether it be UAV or a fixed wing or a helicopter, and essentially reference that to where you are, reference to your data. If you've collected data, you can actually see yourself flying over the area of your project. And finally, data delivery. A major part of any process is actually getting data out and creating formats of data that your clients or your customers need, whether that be LiDAR files, whether that be terrain models, whether it be vector files that are derived from those. And again, that's an essential part of the kind of the global mapper setup. So that's a very brief introduction to the software and the specific components of the software that are applicable for UAV operations. As I promised, I am going to run a very quick demonstration of some of the functionality. This is the interface itself we're looking at now, and we're looking down on a very small section of a power line. As you can see, you probably can pick out the pylons here over on the left-hand side, and if you look, if you squint really hard, if your picture is good enough, you might actually see the power lines themselves. Superimposed on top of this image, I have some point cloud data, and this is the essence of what we're going to use today to extract intelligence essentially from what we're looking at from on high. Now, those of you who have not worked with point cloud data before, what we're looking at essentially are a series of X, Y, and Z points. I'm going to simply select a point at random and show you what information we have with each point. Well, obviously it's elevation in here. We've got a class value, which is a numeric or alphabetic value that determines what exactly that is, a number of other pieces of information as well. Multiply this by, I'm just going to look over here, by 20 million, and you have the array of points that we're looking at on the map right now. Quick look at my metadata, which is essentially information about that file, will show me that the point spacing in this file is about 44 per square meter, so very closely spaced points collected at a low altitude. This resolution of data is going to be essential for performing the process I'm about to show you. Now, this just looks like a random distribution of points, and it is. If I render it in a 3D view, I'm just popping up a 3D viewer window here. Hopefully it'll refresh in just a second. If it doesn't cooperate, it will abort. There we go. So we're now looking at the same data in a 3D perspective. In fact, to make it a little more interesting, we'll pop up the exaggeration just a little bit, and we can see quite clearly now there are above ground features. There are power lines, there are pylons. My objective in this exercise is to extract these pylons, extract these power lines. One other visualization I want to show you, which is essential for many of the workflows, is a cross-sectional perspective. Again, from the top down, it just looks like a random distribution of points. I'm going to draw a profile. Before I do, I want to make sure I've got the appropriate width. I want to bump that up to like 10 meters. No, actually, I'm going to make it about 20 meters. So in other words, it's going to create a swath 20 meters wide through my point cloud and allow me to see exactly what is in that point cloud from a cross-sectional perspective. Once again, pulling my window up from below, you can see very clearly now we have above ground features which are not detectable in the top-down view. Now, let me just remove the profile for the time being. One of the essential workflows when you're working with point cloud data is to determine what each point represents. I want to change the visualization of this point cloud very quickly to visualize by classification. That was that number value we previewed very quickly. You can see in this case all of the points are the same color. I don't have a legend on my screen, but if I did, it would tell me they're all unclassified. As a starting point, what I need to do is identify within this point cloud which points are ground. And we have an automated tool for doing that. I'm just going to initiate this process without taking too much time to explain the process itself. I will limit the extent to just what I see on my screen, just to speed up the processing just a little bit. And what it's doing now is it's going through and looking initially at the return number for each point. If the point has several returns, it will only take the last one. Or if the laser pulses on multiple returns, it will take the last one. When it's defined those final returns, it will then analyze the geometric characteristics of the point in relationship to the points around them, and ultimately determine if each of those points is a ground point. point, and I spoke just at the right length, because what you can see now is a fairly large percentage of my points are now brown in color, which means they are identified as ground. Once again, if I quickly run my profile view, hopefully this will confirm. At the bottom, you can see I have identified ground. Now, if your intent in using this type of data is for any sort of terrestrial or ground analysis, you can simply turn off everything that's not ground and generate a DTM, a digital terrain model, from what's essentially defined as ground. Generate your contours, do the volume calculations based on pile volume, etc., etc. In our situation, we want to take the remaining unclassified points and we want to essentially identify those power lines. And again, there's a tool right up, a pre-configured tool in our toolbar that will allow us to do this. This one tool does multiple things. We can identify vegetation, we can identify buildings, I'm going to uncheck that box, or we can identify power lines, and we can determine various parameters, the minimum ground height, height above ground. Now that we know ground, it will recognize that threshold. Minimum distance from a best fit line would be the lateral threshold from what's recognized as a linear path of points. A little flexibility in there to make sure we have more points, or as many points as we need. Bin size is our sampling area, and maximum height per change per meter. This will allow me to accommodate the fact that we know that utility lines are not horizontal but have a certain dip. So with those settings applied, and again with the bounds limited to what I have on my screen in the interest of time, we will let this run through. And I warn you that when we look at the final result in the top-down view, we probably won't see too much difference, simply because there are not that many points in the 20 million or so that we have in our point cloud that are actually point clouds. So we'll let this show along. I may actually come back to this if it's taking a little longer than I expect. We may come back to this after I run through my second brief scenario. So looks like it's trying to find its ground points first. We'll wait to see if this dialog box goes away, and if it doesn't, again, I thought I chose a fairly small area in the interest of time. There we go, that one went away. I think we're making progress. Calculating my height above ground, again, that's based on the recognition of those linear features. And finally, hopefully that one will depart, and there we go. It's now finding candidate points, and it will ultimately give those a different color. I think if I talk long enough, it will actually catch up with me here. And saving my changes, this is the final step in the process. Now, the result of this, as you will see, is not immediately apparent. A couple of little yellow sections in here that you can see peeking through, and again, the best way for me to visualize this is, once again, with my profile, you can see quite clearly it has identified those linear paths above our ground threshold value. It has picked up some anomalies here in the pylons, but that's fine. We could modify those. In fact, we can edit them in this cross-sectional view. The final step in this workflow would be to extract these as vector features. There's an extraction tool that will create linear features, essentially connecting the dots in a three-dimensional plane to give me those, again, 3D lines that I can ultimately export into CAD, into shapefile, into CAML, whatever I need. In the interest of time, and knowing that Pierre coming after me is going to want some time to talk about his application for this technology, I'm going to bypass that step. But I want to bring up one other scenario here. And again, another version of the software loaded. This is a very close view of what's not immediately apparent from the top-down view, but it's actually a pile of material. I have a point cloud as well. I'm going to turn on that point cloud, and just based on the shading that's applied by default, you can see that top-down view shows me this red, distinct red color indicating this is fairly high ground. My objective in this very short exercise is to measure the volume of material in this pile. Maybe something that you're doing in your workflow, or that maybe your clients are involved in, basic volume calculation, a very simple process. Before I get there, I want to show you a couple of other options we have. We talked about some of the visualization options. I showed you visualizing by classification. You'll notice one here says RGB. Red, green, blue, basically. That's not available by default in this situation. However, there's a tool in the application that will extract the colors from whatever image is sitting underneath and actually apply those to every point. We're looking at about 2 million points, as noted over here on the left side of my screen. Running through that process, very simple. It's basically going to go through and give each point a color value. It appears that the point cloud is gone. It actually hasn't. If I turn off the image, we're now looking at the point cloud as a 3D photorealistic model, and you can see now it is distinctly a pile of material here. Again, my objective being to measure how much is in this pile. I'm not concerned about the trees around the edge, by the way. Obviously, in this case, they're not relevant to my workflow. So, how does this process work? Well, first of all, we need to run this point cloud through a transformation process. Ultimately, we need to create a terrain surface. Again, without going into the particulars here, I'm going to generate a very simple model, a raster model derived from my points. Process is almost instantaneous. What began as points is now raster. And you can see now, again, very clearly denoted here, this upland area, this little mound, I guess you would call it. How do I determine the volume of this? Well, the process begins simply by delineating the extent of what it is you want to calculate. And very roughly, I'm going to outline the extent of that pile. You notice I'm not taking that much care and attention, and it's not critical what I do. I'm simply drawing an arbitrary polygon, no particular characteristics associated with that polygon. Didn't really draw it very cleanly, as you can see, but this is going to form the basis of the calculation, because what we can do now with this ground model in place is we can select that as the extent. I'm just highlighting it to a selected, and run through a pile volume process. Now this is going to happen very quickly, so before I do, I'm going to explain what's going on. The boundary of that polygon obviously sits on top of the terrain. The process I'm about to initiate will generate a terrain surface, essentially a temporary surface, derived from the elevations around the edge of the polygon. Now, we're not going to see that, but that's going to form the basis for what's calculated. It will ultimately calculate up from that level. So this is a good tool to use if your pile is not on a flat surface, it's on an inclined plane. You can still perform the very precise volumetric measurements. So again, going to be a very quick process. Once I initiate that dialog box, we get the results. So I can see clearly here that my pile, the pile of material that I derive from my point cloud, has got the volume noted here. It looks like about 48, almost 50,000 cubic meters. If we look across here, you'll notice a couple of variations here. We've got a cut volume and a fill volume. The fill volume would be areas within the polygon that are actually lower than the arbitrary plane that was created. We're not concerned about those, and that's just simply because of where I drew the boundary. There are areas that dip down below that, that level. So the ultimate value that we're interested in is this cut volume, as you can see. And again, my cut volume, 50 cubic meters of my project, involved me contracting with a company to maybe remove this material, or determining the capacity. You can see it's a very simple process. Now, this same procedure would work in reverse. If I had a trench or an area that would need filled, I can determine how much capacity that is. It would be a negative number. My cut volume would be negative, so I could determine, again, the capacity of my area. So that is a very quick overview of Global Mapper and a couple of practical applications. Once again, questions at the end. Hopefully, if I've enticed you with some of the highlights, this is just the tip of the iceberg. Feel free to ask questions, and we'll get to those at the end. I am going to transition very quickly to a partner. The folks at Drone Mapper have been using our software for a while. Pierre Stromer is going to be coming on and kind of putting what I introduced in a hypothetical context into a more realistic context.
Thanks very much, David. Many thanks to Blue Marble Geographics and Directions Magazine for inviting me and having me speak. This is some interesting stuff that that drones are allowing to be done for commercial use as well as research use. A topic I'd like to discuss is the transition from images that are collected to GIS solutions, and I have a set of examples of how we use this technology and Global Mapper specifically. My name's Pierre Stormer. I'm with Drone Mapper. We produce desktop photogrammetry or image processing software, as well as provide our clients with end-to-end solutions from drone collections through image processing, through knowledge extraction using Global Mapper, for instance. There are three key software elements for producing precision maps. The first one is the mission planning and execution software. It's typically free or very inexpensive, and it allows precision collection of imagery that would then be fed into the second step, which is photogrammetry or image processing, to build or translate the 2D imagery into 3D models and orthomosaics. The last step is extraction of valuable GIS information using a software package like David explained, and we use exclusively Global Mapper. Some key functions for each of these individual software packages. For the mission planning and execution piece, you want to achieve reliable overlaps. You want to be able to trigger your camera with distance traveled, which for whatever platform you're using. You want to be able to control your white balance, your ISO, and your shutter speeds depending on the operational parameters of the platform and the conditions of the imagery collection. There are some optional features that are handy. Being able to cache a map that you previously planned a mission for a remote area is nice to have when you don't have connectivity out in the field. Some of these applications provide terrain awareness so that you can, as you're collecting the imagery over the area of interest, you can maintain GSD or your ground resolution. So the platform actually moves up and down depending on how the terrain below it changes. And then another option is besides traditional nadir or vertical imagery capture, you can complement that with oblique images, and we'll show here shortly what that provides. There's a link I put on this chart that has an interactive spreadsheet that you may use to check out what your mission planning and execution software is telling you. So you'll have to probably, this is a blog page, and it's probably the second post on page 2. So when you get a chance, take a look at that, and you can put in your camera parameters, your operational parameters, and it'll tell you how many images you should be collecting for the size of the area. You can also program overlaps, etc. The second part is what we do, photogrammetry. Some of the key functions are it's nice to have a rapid preview out in the field if you are equipped with a laptop, so you can check your collections and do a preview orthomosaic, for instance, in minutes in minutes in the field to verify that you've got the right type of overlaps before you pack up your drone and leave. Another feature might be resolution scaling for both the digital elevation model and the ortho. Not all jobs need full resolution, especially if you're doing volumetrics like David spoke about earlier. You can live with resolution spoiling and still get accurate results. But you do want to generate low noise DEMs, and you want to limit your artifacts that, in terms of seam lines, etc., that can be exhibited in your orthomosaic. Another nice to have is generation of a point cloud where through photogrammetry you can generate a digital terrain model, and you can use it for other post-processing. Another quality parameter is the accuracy of your latitude, longitude, and your elevation. In some cases, using ground control, you want to have survey quality or near survey quality. On the GIS end, again, specifically talking about Global Mapper here, we're interested in both 2D and 3D large geotiff visualization and manipulation. We want a full complement of analytics and measurement capabilities, of which David showed a few. And we also like to have a wide range of exported formats, so a lot of these products can be utilized in computer-aided design applications, which a lot of engineering construction people use day to day and are familiar with. Um, we deal a lot with surveyors, and typically what happens is we get ground control where the client is interested in a highly accurate map, both digital elevation model and orthomosaic. They provide the ground control points, which are shown on top of this map on the left-hand side as little red dots. And the coordinates are usually sent to us in state plane, or it could be a local coordinate system, or it could be a country coordinate system. And we process in using UTM World Geodetic System 84. So we have to convert those, and one of the problems that can occur is that you incorrectly convert them. So what we do is we use the transformations that Global Mapper provides to take, let's say, a state plane, which is shown in the tables to the right, convert that to UTM, whichever zone it's in, WGS 84, so that we're ready to process. And then what we'll do is we'll take a screenshot of an area with the ground control point, send it to the client, and verify that this indeed is the scene that they want processed, that we didn't put it in the wrong place on the Earth, if you will. After the photogrammetry processing, we generate a digital elevation model and an ortho, and shown to the left is the orthomosaic overlaid on the digital elevation model with the same ground control points previously shown. We use this to compare the ortho and the digital elevation model rendering, the latitude, longitude, and elevation position of the ground control compared to the ground truth coordinates that were sent to us. So on the right-hand side, you can see two blow-ups of two different ground control points. In this case, they are white L-shaped targets where the inside of the L has been previously surveyed precisely on the ground, and we measure the position of that point on the ortho and the digital elevation model and compare it to the true surveyed ground coordinates to verify that the specified accuracy has been met. Okay, here's an interesting example. This is a volumetrics, sort of a follow-on to what David was speaking about on the last example he showed. This is a combined reservoir. It's called Young's 1 and 2 at about 10,000 foot on the Grand Mesa. It used to be two separate Young's 1 sitting here, Young's 2 reservoir sitting here, and there was a dam between the two, which you can see. Hopefully it renders okay. You can see a breach in this dam structure. Now the real dams are down here. But what we did was we flew this, collected the images, generated the digital elevation model and the orthomosaic. What you're looking at on the left-hand side is the digital elevation model with a set of contours with one blue highlighted. And we use those to look at capacity for various water elevations. And the table shows the reservoir volume in acre feet and the surface area for the various contours that were digitized. And these measurements were made in October of last year. We came in at 794 acre feet. We talked to the water board, and they dug into their records and they found that in 1950 the capacity was estimated at 797 acre feet. So we were sort of amazed that 60 years ago these guys really knew what they were doing up here in the high country. Here's another volumetrics. This one has a little twist to it. This is a coal mine out here in western Colorado. The top illustration is a point cloud of the coal being stacked on the ground via a conveyor system. So this is a longwall mine that has conveyors that run into the depth of the mine and bring the coal out as it's being mined. and deposits the coal on the surface of the Earth as a stockpile. There's a solids model shown below, which is a 3D model that was generated using two different surface models. One was the image coal surface, digital surface model or digital elevation model that was collected at the time this imagery was taken, plus a bare ground reference surface, which is controlled by a set of ground control points. And we use a function in Global Mapper called terrain combining, where the reference surface is subtracted from the collected imagery surface that's generated, so that they get a very accurate temporal evaluation of what their inventories look like, and it's always against the same reference. So we minimize errors by always comparing it using that reference surface. Because of the obstruction that the conveyor surface has over a portion of the pile surface, we utilized a combination of not only vertical images but obliques. So we used an acquisition software that allowed flight of an orbit. So we would fly a grid pattern to collect the vertical looking or the nadir images, and we complemented that by flying an orbit and shooting at somewhere around roughly 45-degree oblique angle to try to look and peer under the structure to get better resolution of the surface. And then we process that together. You still have some remnants of the high elevation structure in the digital elevation model, and in that case we use Global Mapper to remove or classify those high elevations that are portions of the conveyor structure. They are removed, and then triangulated networks, irregular networks, are built to interpolate the surface where the conveyor structures have been removed. So it's an interpolation, but it's pretty close. It's not bad. It's still an estimation. Okay. These are a set of images that were taken in near infrared. This is an application for precision agriculture. This is a research field. These images were processed by us. They were provided courtesy of a company called Pravia, and they funded the work. On the left-hand side, you see week 1. So this is early June, near-infrared ortho, and the corresponding green NDVI. NDVI is the Normalized Difference Vegetation Index map. And the copper color shows higher vegetation robustness or health than the yellow and the green. On the right-hand side, about 2.5 months later, week 10, late August, you have the corresponding near-infrared ortho, and you can see lots of growth in the research field, as well as its green NDVI. This facility was investigating genetics, and what we did, what was kind of unique, was we used spectral targets that served as both radiometry for spectral reflectance, as well as precision position. And each week it was flown so that you could compensate for lighting changes, atmospherics, as well as sensor gain, drift, etc., from week to week, so that you had a really good temporal change detection method over the full 17-week research period. The NDVIs were generated in Global Mapper, and it's called green NDVI because we use the near-infrared and the green bands to compute the NDVI.
Pierre?
Yes, ma'am.
Hi, just wanted to touch base. We only have about 5 more minutes in our session, and I know that you have some good resource information, for folks. So maybe if we skip ahead just a smidge and we can tackle just a few questions that folks have.
Okay, I'm going to skip this chart. These are just 3D models. And I'm going to skip this. This will be in Directions Magazine's video. This is an interesting, one of my favorite features in Global Mapper is a 3D fly-through. So we'll wait to see that once the production is complete. And to wrap up, I just wanted to comment that you can do this mapping. I saw there was a question earlier. The total investment to start to do precision mapping is on the order of $2,000, and that covers the hardware and the software. And that wraps me up. I'm sorry I took too much time.
No problem at all. We just want to be sure and at least get to a few questions. And folks,
Okay.
Listen, we're going to share all of this information as well as any questions that you have and we didn't get to. So I'm going to turn it over to Rich real quickly, and we'll see if we can't work through a few questions.
Okay.
Great. Thank you so much, gentlemen, for your presentations. They were very educational. We've had a number of questions that have come in regarding recommendations for various brands, specific products, and so forth. And while Directions Magazine and the Geotech Center don't endorse any of these products specifically, I will refer our webinar attendees to some of our references and some of our resources from even last year's presentation. So you might be able to find some of the recommendations there for different types of products and different types of instruments that you might be able to use. A couple of questions here that are coming in specifically about the global mapper. And one of the questions was, I'll just hit these in rapid fire, and David, maybe you can help me with these. Can
Sure.
Global Mapper correct tilt through orthorectification?
Yeah, I did actually see that one come in. The easy and short answer to that one is no, and that's based on the technology as it is right now. This product is constantly being updated. That is one of the things that's on our wish list. There is a rectification tool, but not orthorectification in the current setup. But I guess the moral of the story is watch this space. That hopefully will be coming along soon.
Great. There was a question that came in about how much does the software cost, which I see we've basically answered that question here. But are there any open source software that you know of that can conduct point cloud analyses?
Open source, I'm not sure of any open source, and obviously, and you talk about, not endorsement, but obviously I'm affiliated with a company here, so I've got to be very careful what I say. There are other tools out there. I mean, obviously, the rapid increase in the availability of point cloud data has led to an increase in the availability of software. And I will go back to the cost just in terms of the actual software component of that. Global Mapper is about $500 to start. There is an add-on for LiDAR specifically, so if you need to add that on, that will give you the full processing capability I showed you. In terms of actual open source, again, not anything I'm aware of as far as point cloud processing is concerned.
Right, and the price you quoted there, certainly a reasonable cost, and certainly something that as we watched you do that demo has lots of capabilities. Have you observed LiDAR penetrating water, in other words offshore benthic resources?
Bathymetric.
Yeah.
Near shore, yes. Obviously, LiDAR, or the laser-based collection process, is light and dependent on reflected light. So further out you get, obviously, the less you're going to be successful. But it is increasingly common, especially for near-shore applications. I was actually working with some data just a couple of weeks ago on a coastal erosion process, which had partly bathymetric, near-shore bathymetric data. So it is becoming increasingly common. Technology is improving, and the accessibility of that data. So yeah, watch this space. It is an ever-changing technology, and
like everything else.
That was not the case, but yes, it is now. Yeah.
Right. And can Global Mapper files be exported to CAD?
Absolutely, yeah. It is completely interoperable with virtually every platform. DWG, DXF files can be exported, shape files obviously as well. So 250 formats is our count. We haven't actually sat down and confirmed that anytime recently, but it's over 250 formats.
How about working with thermal imaging or video, in other words, radiometric data?
No, we haven't done any work specifically on that. I would need to do some more research on that format to see exactly what would be involved. I know we'll get copies of these questions ourselves, so I may follow up with the person who asked that question directly after I talk to maybe some of our development staff here to see what would be involved in that. So we'll maybe take that one offline, but to my knowledge, as of right now, no.
We've already talked a little bit about cost, and this is probably available on the website that everyone can see on the screen right now, but what about, do you have not-for-profit pricing that might be available to someone who's interested in
That's always a tough question. I should have had some of my sales colleagues on here to talk about that. If it was up to me, I'd be giving it away. No.
Yeah.
We have academic pricing. We have a special licensing model for academic use, and I know this is being used in many schools and colleges, again, because of the accessibility, low price point, and we like to think it's a relatively easy to use application as well. Not-for-profit, we don't really have a pricing structure specifically addressing that. Again, I'm very cautious in what I say here because I'm not directly involved in the actual selling process. So, but certainly contact us, and we'll find out what you're interested in, and we can come up with a pricing model that hopefully works for all concerned.
And again, Pierre's contact information and David's information has been flashed up on the screen. We'll share all this with you. Back to you, Barbary.
Well, I just want to thank everyone for their patience. You know how technology goes. Everything worked perfectly for our first 2 sessions, and we had some audio challenges here. So we have recorded all this, and we'll make this available to you online, so just keep an eye on your inbox. We'll also be in touch with your many questions and share these with our presenters so we can take good care of you. Go have a great rest of your day and tell a friend about directions. We'll see you later.
Bye safe.
Okay, bye-bye.